I'm WanderingGlitch, and this is leaking kernel pointers. All right, I'm a reverse engineer, vulnerability analyst, and exploit developer with the Trend Micro Zero-Day Initiative. We're recently acquired by Trend Micro, but the Zero-Day Initiative, for those who don't know, we buy vulnerabilities, and as one of the guys on the program, I analyze them and then try to find variants, and then we report them to the vendor so that they can get it patched. That's all free to the vendor. We only just pay the researchers. Today I'm going to be talking about leaking of Windows kernel pointers, specifically a mix of code pointers and data pointers. The example I'm going to go into is a data pointer leak. Most of the bugs that I found are uninitialized buffers, but the one I found, or the one I'll be talking about and focusing on, is an accidental pointer leak. And as for why, I found I only got 8 CVEs. It's actually part of the back of my shirt. You'll notice that the bottom 2 are actually much lower number than the others. It's because I submitted those as kind of a test of the water. I didn't quite know if Microsoft really cared about local information leaks in the Windows kernel, and it turns out they do, despite having some deficiencies in other areas. Once that happened, they seemed to be interested, and so I found a few others in other areas and got those patched as well. As a result of actually, I think, CVE 2015 77 and 94, but more specifically 77, basically every Userland callback was modified and buffers were finally actually initialized to 0. Now I'll go into what Userland callbacks are, because they're the crux of most of the information leaks that I've found. So they're implemented in core NT. If you're looking at actual modules, then this is going to be the module NTOSKernel.exe. In Userland, this is managed by NTDLL, but the only code that actually makes use of this is the Win32k subsystem. The whole point of this is to allow kernel code to make callbacks into Userland code. And there's a table that's described in the thread information block that allows you to index in and call any Userland function that already has hooks set up. As you can imagine, moving from kernel to Userland can be kind of tricky, and it's historically been the source of a lot of bugs. As far as its official purpose is within the Win32k subsystem, it's primarily used for passing of window messages and dynamic data exchange, which also uses Windows and window messages. The way it works is NTOS kernel exports a function called KEUserModeCallback. Just as a brief background, any function within NTOS kernel that starts with KE in the name is an exported function. I don't know that it's kernel export, but that's how I've always interpreted it. Anything that starts with KI is an internal private to that module function. And that's ultimately what KEUserModeCallback calls, a function called KIUserMode. What this does is it sets up a fake stack and it returns to it so that it then returns to KEUserCallbackDispatcher. All that does is set up stack and set up the argument so that it can then context switch back into NTDLL and go from there. And the important takeaways here are that there are 5 arguments that get sent to Userland. A callback ID, which is essentially an index into a function table, an input buffer and an input size, and then a pointer to an output buffer and a pointer to an output size. Once we're back in Userland from the kernel call, we make it into NTDLL KIUserCallbackDispatcher, and that's, as I said, it uses the callback ID as an index. The function table is located in the tib. Actually, it's in the thread info object. User32 initialization will, as part of loading user32 and making any user32 call that eventually makes it into Win32k, your thread will get all those pointers initialized for you. Specifically, you'll get it pointing to user32's APFN dispatch, which is hard-coded in the module itself, but you can point that to whatever you want. Once it's indexed and gotten the function to actually call, it makes the actual call and lets it do its own thing. Once the callback has done its work and it's either failed or succeeded, whatever, a call to user32's XY callback return is done. This function never actually returns. What it does is it performs an int hex2b back into the kernel, And if you look at the kernel's input interrupt descriptor table, you'll see that that ends up calling KI callback return. I don't quite know why they do it this way instead of making a sysenter or an int-hex2e, as they do for all other syscalls, because you could use use a syscall ID for NT callback return and do the exact same thing. I know there is a reason. It's probably legacy and historic, but I don't know. So if anyone happens to, I'd be curious. As I mentioned before, it's historically been the source of a lot of bugs. A lot of use after freeze due to lacks of locks on objects. So an object will get dereferenced, you'll store a pointer on the stack, you'll return to userland, and then userland will do something to destroy that object, but you still have a reference to it on the stack, on the kernel stack when you return back. So that they fixed that with locks. The problem with that were ref count bugs, which resulted in a limit of, I want to say 15 or 16 recursive userland callbacks. So after that, it'll just refuse to make any more userland callbacks. Most of the most of the locking issues are handled by the use of something called thread lock, which is stored in the kernel side thread info structure. And that's basically I think an 8-byte or a 2-pointer size value structure that stores a current pointer to an object to free and the next pointer in that list. It's just a single linked list. That way, if the thread happens to get killed for any reason, it'll get cleaned up upon destruction. Another type of a bug that's been found a lot in the userland callbacks are time of use or time of check, time of use bugs, and those are still probably prevalent, but those will just be hunted and pecked. Another piece of background that we'll need to know for the userland callbacks, because they all heavily use them, are window objects and messages. And window objects are massively prevalent in Windows. Actually, if I break out of presenter mode, this, that's worthless. If you see a scroll bar, like on the right side of your browser or any window, that is its own window. If you see a window itself, that's its own window. If you see the X or the minimize button, those are all windows. There are a lot of different types, and in the kernel, they're all referenced as pwnd, P-W-N-D, pointer to a window. In userland, you get a reference to them with a hwind, which is just an integer describing a value in a handle table. For our purposes, it's essentially just a D word, and it's easy to come up with invalid values, which will be important later. Another thing about Windows is that you can communicate with them with restrictions from any process or any thread using window messages. And this goes through the kernel and possibly context switches into another process or into another thread if you're calling from the same process. You can get input and output. You can also have window messages that are purely handled in the kernel, and there are other window messages that are purely handled in userland. You can also have some that are kind of a hybrid that depend on the window type that you've specified. So now I'll go over CVE 2015-0094, and this was the first info leak I found. It's a accidental code pointer, or a data pointer leak. And I found this actually not as a result of bug hunting so much as trying to understand userland callbacks. I didn't understand any of how it worked. It all seemed like magic to me, and so I just started reversing. For whatever reason, this particular window message is what I first found. So the way userland callbacks are handled specifically for window messages is you have two sets of functions within the kernel. You actually have a separate entry point, but there are a couple of entry points for them. If you're going to send the WM_NT_calcSize window message, then you'll first end up hitting NTUser function inout NT_calcSize. That's solely responsible for sanitizing input arguments. Specifically, if any window message takes pointers to userland data, it then copies it into kernel land, because if you're going to context switch to another process, that all will be invalid. Additionally, if you're going to depend on any userland data, they could potentially mess with it while you're looking at it or doing anything and cause bugs. Once that's gone through, it then goes through to the actual window procedure within the kernel. That window procedure is going to depend based on your window type. In this case, I was triggering it so that it was forced into userland, and it was solely responsible for calling whatever my Windows window procedure was. From that point, it then goes to sfn in out NC calc size. This function and all the other functions that start with sfn are solely responsible for marshaling the data so that it can then be sent to the userland callback and get handled and interpreted the way it's supposed to be. So the vulnerability itself, the WMNC calc size it specifically stands for non-client calc size. It's used to calculate a Windows client area, and in this case, the result is completely dependent on whatever the client wants to say. And client in this case means the userland code that owns the thread or process running the userland code that owns the window. There are 4 arguments that you send whenever you send a window message. You send the handle to the window, you send the message itself, and then you send what's called a W param and an L param. The W param in this case is a Boolean, but it can be any value really. Typically, if you're going to have some sort of userland data, then it's going to be in the L param. In this case, you can see that the L param actually will vary in type based on the value in W param. So if W param is non-null, then NC calc size params is the type that is expected in L param. If it is null, then a rect structure is expected. Both of these are documented. I didn't actually know this at the time because I was just reversing and not hoping that Microsoft documentation was present or accurate. But both of these are documented, and it actually makes a lot more sense why the vulnerability exists once you see it. So here are the data types. So if you have a rect structure, you have 4 longs. If you have an NC calc size params, structure, then you have 3 rect structures, so 12 longs, followed by a pointer to a window pause structure. And that's ultimately the bug right there. You can't see it without the actual code. The Windows pause structure has 2 hwins, 4 ints, and a uint. None of that data is at all important for the bug itself, but it just ends up being a little useful to know. The whole reason the bug exists is that when the NTUserFN in-out calc size function runs, it copies the NC calc size param structure into the kernel stack. And because there's a pointer in that structure, it copies the structure that's pointing to, the window pause structure, and it allocates it adjacently. It then updates the pointer in the NC calc size param structure to point to the kernel copy. And the whole issue is that once it goes back to send it into userland, it doesn't nuke that pointer, and so you end up with a data pointer leak. Here is some rough pseudocode explaining basically what's going on. So you have 2 allocated structures, the NC calc size params and the Windows pause structure. Neither of them are 0 initialized, which is a very common thing within all the NTUser functions. And you then copy from the L param all the data from userland, and then from the userland's LP pause structure into the pause structure in the kernel. Then you update the pointer, and that's about it. Using this, you can leak an address on this kernel stack. You can use this because it's at a static offset from the return pointer to modify that if you have a arbitrary write what where. You also, because it can be kind of annoying, you control the contents of the 28-byte window pause structure, but you also control the 3 rect structures in the NC calc size param structure. So you have a lot of data that you can just put on the stack and control and use it in any way you see fit. For example, a RobChain. That is pretty hard to see. So there's a line over there in blue, and it just says move EBP plus var 30, EAX, and right above it you see an LEA EAX. That is where the pointer to the kernel stack is getting added. And this next slide is the hex arrays decompilation, which should make it ever so slightly easier. In the second to last line, you see V21 at offset 48 is being set to the address of V14. In the SFN, in the Marshaling code and SFN in-out NC count size, you can see here that this code is responsible for copying the data back into a structure, or copying the data into a structure so that it can then marshal it back and send it to the process. The main takeaway here is that there is no zeroing out of any buffer or pointer or anything. It's just copying data as is. And here again, you can see that all we're doing is copying the size of the structure into an offset and then copying the size of the window pod structure into an offset. And then later on in that function, we are sending that in a call to KE user mode callback, in this case with the function ID of 21. So altogether, all we're going to have to do is create a window and then hijack the WM NC calc size handler. There's actually 3 ways to do that. I mentioned that there's a pointer in the tib. We can replace that with our own and just have our own function table. That would work. There's really nothing interesting or complicated about that. The only thing is we have to make sure that all the other values in it match up to whatever is in user32's APFN dispatch. Otherwise, we could get crashes and we may terminate early. We can also modify user32 APFN dispatch, or at least our copy of it within our process. That could also work, but if you have a process where you have a bunch of other windows, this window message may legitimately get hit, and that could cause trouble for you. We could also hotpatch the WM NC calc size handler itself in user32, and that's ultimately what I did. This means you're then completely version dependent, actually as does a APFN dispatch, because you have to know the exact offset into user32 that this occurs. It also means that any function or any window message that results in a call to WM NC calc size will end up hitting your code. For the proof of concept, it's not a big deal, but if you were writing a full chain exploit, you would not do that. The only thing the handler really does is it saves the value of the input buffer at offset hex 48, and it just saves it off as a D word and references it later. And then it just continues on and allows execution to continue back into the kernel. The PocketSelf is a Python POC that I'm going to show you. It's not the entire thing, but it's the most of it. For example, I'm skipping out on some initialization code to set up syscalls and whatnot, also to get executable buffers, but for the most part, you'll see it. The main reason I started doing Python POCs is actually because of this bug, as I found that Microsoft, if you give them an exe or DLL and you give them source, they will end up distributing that exe or DLL as part of map. And if you happen to have any sensitive usernames when you built the file, that'll be in the file as well. And so I've only started doing Python. I occasionally will only give them a source file, but it's easier just to give them Python. This is the entry point of our replacement buffer, a replacement function. The main thing here is we're getting the address of our kernel stack address variable, and that's just going to be a D word somewhere in memory. And all we're doing is we're taking offset hex 44 and writing it to that address in memory. Here, we're just setting up the values so that we return cleanly into back from the userland callback. And then we're essentially just stealing the contents of user32 xy callback return so that we int to be our way back up. And then at the bottom, I'm just getting a replacement buffer to then modify the pointers with. Here, it gets a little messy. I'm grabbing user32 and load library. It, in theory, only returns a handle, but as of 32-bit Windows, it returns an address. And so I'm using that. I know the offset to the in-out NC calc size function. And I'm just replacing that and basically just adding a jump detour. From that, I'm then modifying it and actually putting it in place. And then I'm calling NTUserMessageCall. I kind of glossed over the entry points to the NTUserFN functions. NTUserMessageCall is one of the main ones. Anytime you send a message, it's going to hit that. And there are a few extra arguments. The main thing to consider or keep in mind is the first 4 arguments are the same 4 arguments that I mentioned earlier. So the handle to the window message, wparam, and lparam. The last, the second or 5th argument, address of result buff, can, for this bug, completely be ignored. The next one is important in that this is documented in a loose manner as function ID. And this is where we're specifying which window procedure within the kernel we want to hit. So in this case, we're going with XXX wrap call window proc. And all that means is that we want to hit the window procedure that will result in calling our userland function. The XXX is a Windows nomenclature for whenever any function may return back into userland code. It's basically a sign that, hey, if you're going to call this, make sure all your locks are in place properly. And then the last one is ANSI. That's just a Boolean specifying whether or not you're using wide character strings or not. So this POC will return cleanly. It'll then leak the kernel stack address. At this point, it's actually pretty useless. You would probably, if you were going to write an exploit, you'd actually want to modify this guy to do more interesting things here, because you already have the kernel pointer. You already control the contents of the data it points to, and that's when you'd actually want to use it. You may return back so that it starts going to your stack or something if you had a write what where, but you'd still probably do it there as opposed to where I have it here. So as far as the patch itself, it was done in a pretty straightforward manner. It's just nulling out that value before sending it to userland. It's just and 0, and you can see that it's just setting that value to 0, and then everything else is completely the same. And that is about it. I have more. I will probably give a lightning talk at the Ritz if you're interested in another uninitialized buffer. Every userland callback was failing basically completely to do any initialization of any variable. So it would allocate space for it, but it would only use, say, I don't know, 2 D words out of a 10 D word array, and you'd end up leaking a bunch of data. Microsoft did end up patching basically every single userland callback to the point where I found nothing outside of a couple of unrelated bugs. And it's actually one time where they were pretty nice and proactive. They actually seem to care, and they're trying hard to remove code and data pointers from userland. And that is something that they're interested in, so it was kind of nice to see. And it was especially nice that I found any bugs, given that I was only trying to reverse out and understand the kernel. And with that, I think I'm done, unless anyone has any pressing questions. What's up, Brandon? Yes.
So how easy would it be to detect that kind of pattern using static analysis of the binary?
With static analysis of the binary, it's a little harder solely because it's leaking in one area and then not leaking in another. That's actually a fantastic question, in that we have an external dev on our team, and he stated that, so if you look at the Windows kernel, there are, specifically the syscall entry points, there are a ton of uninitialized buffers all over the place. There are a lot of them that are completely worthless, but from what he was saying, this is a design decision for performance. It ends up being a terrible design decision, but it's solely for performance that they're not going to do it. They have research that's far, far more advanced than what I've heard elsewhere, and I would have thought that they'd be able to find these and get them fixed, but I've not seen any evidence of that.
I think that's it for questions. Give it up for Jazel WanderingGlitch.